Today we are going to carry out a step-by-step biomechanical analysis of the breaststroke swimming technique. The test subject will be Valentina Bernal, and the video was recorded during the swimming pedagogical field trip carried out in conjunction with the biomechanics course. The main objective of this analysis is to observe how the movement is technically executed and to explain all the biomechanical variables involved during a continuous 200-meter swim. To begin a biomechanical analysis, it is important to divide the movement into different steps. This allows us to better understand each piece of the technique, identify how the body moves, and analyze the force, muscles, and biomechanical principles involved in the swimming performance. Step 1. Identify the technique. The first step in a biomechanical analysis is to identify the type of movement being studied. In this case, we are analyzing the breaststroke technique. This stroke is considered a cyclical movement because the same sequence of actions is continuously repeated throughout the steer, swing, glide, arm, pull, recovery, kick, and braiding. Step 2. Observe body position. After identifying the technique, we observe the swimmer's body position. In biomechanics, posture is essential because proper body alignment reduces water resistance and improves movement efficiency. Here we focus on maintaining a horizontal body position with extended arms and aligned legs to favor aerodynamic displacement. Step 3. Identify the movement pace. Glide pace. In this pace, the body remains fully extended to take advantage of the movement generated the previous kick. Outward arm sweep. The arms move outward, performing shoulder abduction. Inward ball propulsive pace. The swimmer pushes the water backward to generate forward propulsion. Arm recovery. The arms return forward while the legs begin to flex, preparing the kick. Bracket stroke kick. The legs perform a fast and explosive extension that propels the body forward. Breathing phase. The hair rise during the pole phase to allow inhalation before returning to the water. Step 4. Analyze temporal variables. After identifying the movement phase, we analyze the temporal variables. This includes total execution time and split times for each segment of the swim. Valentina completed the 200 meters in a total time of 6 minutes and 40 seconds. The swim is also divided into 25-meter segments to observe possible changes in speed, fatigue, or rate variations through, throughout the performance. Step 5. Analyze temporal spatial variables. After analyzing time, we study the relationship between distance and time in order to determine temporal spatial variables such as average speed and cycle frequency. Step 6. Identify the force involved. In biomechanics, it is also important to identify the force involved in the movement because they explain how propulsion occurs in the water. Propulsive force generated by the arms and legs pushes the water backward. Water resistance occurs when body element is lost and frontal resistance increases. Buoyancy helps keep the body near the water surface. Gravity acts constantly downward throughout the entry movement. When discussing gravity force and motion, we must also relate the analysis to Newton's law of motion. Step 7. Apply Newton's laws. First law, inertia. During the glide phase, the body continues moving due to inertia until another force modifies its motion. Second law, the greater the force applied during the kick, the greater the resulting acceleration. Third law, when, when the swimmer pushes water backward, the water produces an equal and opposite reaction that propels the body forward. Step 8. Identify muscle involved. The next step is to identify the main muscle involved in the movement. Arms. During the pull, muscles such as the pectorals major, latissimus dorsi, and deltoids are involved. Legs. During the kick, the main muscles involved are the quadriceps, hamstrings, and gluteus maximus. Step 9. Analysis neurophysiological elements. We must also consider the neurophysiological system that coordinate the movement. Cerebellum coordinates synchronization between arms, legs, and breathing. Proprioceptors provide continuous feedback about body position in the water. Muscle spindles regulate muscle strength and contraction prior or the keep. Identify biomechanical principles. Finally, we identify the biomechanical principles observed during the execution of the technique. Coordination of partial impulse. The kick is coordinated with the arm recovery phase to maintain continuous propulsion, pre-stretch, prior elongation, flexion before the kick allow stronger muscular contraction, optimal trajectory. The curved underwater arm movement improves impulsion efficiency, stable center of mass, maintaining a horizontal body position, reduce frontal resistance. Step 11 Conclusion. In conclusion, Valentina demonstrates a relatively coordinated and stable breaststroke technique. Throughout the 200-meter swim, the biomechanical analysis shows good synchronization between arms, legs, and breathing, as well as consistent cycle frequency during most of the performance. How, However, improvements can still be made in maintaining a more aerodynamic body position during braking and extending the glide phase to reduce energy expenditure and improve overall efficiency.
In temporary variables, to calculate them, the total time of the test and the partial times of each segment are taken. In this case, the total time recorded was 6 minutes and 24 seconds. For temporospatial variables, the average speed is found, which is obtained by dividing the distance traveled by the total time spent, getting approximately 0.50 meters per second. For frequency, complete stroke and quick cycles performed every 25 meters are also counted. The average was 18 cycles, which indicates technical stability during much of the route. In the topic of forces, here you can see how the arms and legs generate propulsive force by pushing the water backwards. Regarding Newton's law, during the slide, the body continues to advance due to inertia, and during the kick, the acceleration of the movements is generated. At a muscular level, different muscle groups of the arms and legs participate in these movements to generate propulsions. Deltoids, triceps, lats, trapezius, lumbar, abdominals, glutes, hamstrings, quadriceps, adductors, and abductors. Continuing with this analysis, I am going to demonstrate each of the phases and movements that are part of the chest technique in order to observe how the movements in the water works biomechanically. First, I am going to show the general movement of the chest stroke. This movement is characterized by the fact that the arms and legs work in a coordinated and repetitive manner throughout the entire movement. Now, I am going to show the initial body position. The body should be kept horizontal and fully extended in front and legs together to reduce the resistance of the water and facilitate movement. In these phases, we feel the sleep, where the body remains fully extended to take advantage of the momentum generated by the kick. In the external sweep, the arms slowly open outwards, preparing for the next pull. Already in traction, the arms push the water backwards to generate propulsion. In recovery, then the arms return to the front again while the legs prepare for the kick. To execute the kick, the legs are flexed and then quickly extended to propel the body forward. Regarding breathing during traction, the head comes out of the water swiftly to inhale. In the neurophysiological elements, it is found that from the central nervous system, the cerebellum, the proprioceptors, the basal ganglia, and others allow to maintain a coordinated execution of the movement between breathing, the kicks, the stroke, maintaining the rhythm and stability. For biomechanical principles, it is observed how the stroke and the quick work in coordination to maintain continuous movement, maintaining kination and modulation of movements, preparing the muscles before their contraction and continuing with the opposite relation in each phase of the still without forgetting the displacement of the center of gravity. Finally, biomechanical analysis allows you to understand how each phase of movement influences efficiency and displacement in the water.